welcome back. So, this is an extension of the previous lecture and this is regarding the digital hysteresis control. So, in this lecture we will show that analog hysteresis current control, then how does the mixed signal hysteresis control look like and their control waveform, and finally what is the architecture of mixed signal hysteresis control and then what are the benefit of mixed signal hysteresis control. So, we know about the analog hysteresis control and that we have discussed in sufficient detail, and that means the inductor current should be retained within some peak and valley. So, in this case we are talking about the Iref and delta. So, that means if this is your Iref and that means this is my Iref and this will be my Iref minus delta IH, and what we are going to do, inductor current will remain within this band like this. Yeah. So, this is like this, and that we have discussed, and it will accordingly generate the gate signal. Now, when you close the digital loop, then this inductor is in analog and this is in digital. So, you cannot use a mixed domain thing directly. So, you need to have a D to A converter, and that we have also discussed in the previous class. So, when you consider a D to A converter, if you straight away replace, that means you need to insert D to A converter for these two references. But why? Because it is already digital. So, this is also digital. Because why we kept delta IH in digital? Because we need to adjust the delta IH, because we know this is one of the parameter or degree of freedom to actually control the switching frequency. So, if you want to control the switching frequency, you can simply adapt the hysteresis band, and that is very well known method, and that can be very easily accommodated in digital control, right. But use of two D to A converter and two analog converter is practically not acceptable. Okay, then what is the way? How can we reduce both DAC and comparator? So, you can use a time multiplex operation. That means the peak is and the valley, because we are talking about the peak and the valley. So, this is my peak and this is my valley, and I want to force the inductor current to be within this peak and valley, right. And how are you setting peak? That is in your hand. So, I can set either peak equal to my reference, which is the output of the controller, that means digital voltage controller, then the value will be simply Iref minus delta IH, and this configuration is a peak control configuration. That means we are directly controlling the peak current. But if we want to do valley current mode control, that means how do you do that? That means here remember we need a select line, right. So, this is my select line, and the D to A converter will accordingly adjust the output, and here the digital logic will be there. So, how does it work? Okay, suppose I am talking about this is my peak. So, let us say this is my some Ix. Okay. So, let us say this is my peak, this is my IP, let us say which is my Iref. I am talking about this, and let us draw another waveform which is my I valley. This is my I valley, which is my Iref minus delta IH. Okay. Now, how does it operate? And we want to draw the inductor current. Let us say inductor current is going up. During this time, when the inductor current is rising, I need to compare this inductor current, and this is a VA. That means if I take VA is nothing but what? It is the analog version of the IX. So, what is my VA? My VA should ideally represent, this is my VA, this is like my VA. Whenever there is an intersection, then my VA is changed to what? I valley, and then inductor current will start falling because the comparator changes. So, it start falling, sorry. So, it should start falling like this, and since if I continue this structure, that means if I continue this waveform till this point, then again it goes high like this, and again the inductor current will continue to follow this path like that. So, that means basically I am changing this VA, which is my VA, with muxing operation. That means we are changing based on how, because if the inductor, that means we have to detect whenever the inductor current try to cross this VA, we will get a positive edge, right. That means when it goes from lower to higher, we will get a positive edge. Similarly, when it goes to higher to lower, we are trying to find a negative edge, that means falling edge. So, when the rising edge come, we will change this mux from VA will now get configured to the valley current, and when the falling edge come, the VA will be configured to the peak current. So, by that way it will keep on changing, but in practical converter it is not so simple, because there will be noise in the current. Each case there will be noise in the current, and you need to provide some dead time. So, it is, in hardware design point of view, this is somewhat complex, but if we can do it, then only one D2A converter, one comparator is enough, and the digital logic has to be configured in such a way it will command that how the select line should behave and what is based on the comparator output, how to take the decision. And this is a comparator output, it is not the gate signal. Okay. And this aspect have been discussed in this paper. Now, we can set it as a peak current reference, as I said. So, this you keep it as a reference current output of the controller, and this is the delta H, and I have discussed that you can configure this valley and peak in such a way this VA will change. So, that means if I want to draw VA in this waveform, suppose this is my VA, right. At this point my VA will change here, VA, again my VA will go here, VA. So, this waveform is my actual VA, which is this signal, and based on this output of this comparator output, our digital logic will configure whether it will be turn on or turn off, and that accordingly it will select, and that means using one comparator, one DAC you can implement. So, this is a peak current mode, then you can do valley current mode, you can do average current mode. That means here it is just a matter of how are you changing here, because ultimately this is your peak and this is your valley, correct. So, this is your valley, sorry, yeah, this is your I peak and this is your I valley. If you want to change to valley, then I will simply take the compensator output as a valley, and peak will be plus that valley current plus delta I ref, delta H. This is exactly what I was showing. Here also again if you see, this logic of VA will remain, it is QC, and this logic of VA will be again like this, it will configure here, it will change to here, again it will go here, it will go here like this. So, this waveform is my VA waveform, which is nothing but here. Okay. So, because it is a single comparator and the digital logic will accordingly adjust. And if I ask you how to do average current mode control, so this is my peak and this is my valley. So, what I will do? I will simply take peak equal to, if this is my compensator output, that means if this is my, this point is my, let us say controller output, I will set icon plus delta IH by 2 and I valley is icon minus delta IH by 2. By that way we can do average current mode control. What are the benefit of this? We have discussed, if we talk about analog hysteresis control, the inductor current ripple was reflecting here, right, sorry, the output voltage ripple, and as a result we know that actual inductor current ripple and the hysteresis bands were different, and that was sensitive to the ESR of the capacitor, that was sensitive to the controller parameter. So, there are many other factors, but in digital control, if we are using event based sampling, we are taking only one sample for the whole cycle. So, even though there can be ripple in the analog, that means actual output voltage, but we are taking just the sample point and hold it. That means the controller will not see the ripple artifact in the in this logic. So, it will remain constant for the whole cycle. So, your peak and value will remain constant and inductor current will simply follow that path. Only the concern is that you have to ensure the cycle by cycle stability is retained, then at steady state these two will be fixed. That means, it will look like a peak here and valley here, and current will simply follow this path. So, in that case the delta IH, which is the hysteresis band, and the current ripple, which is this particular current ripple delta IL, they are same. Okay. So, that means, one of the benefit is that the delta IL is nearly equal to delta IH. So, it is insensitive to controller parameter, it is insensitive to ripple parameter ESR. Another figure, so if that is true, then it makes the design simple, because we know delta IL. So, that means, what is delta IL? So, delta IL for a buck converter or any DC-DC converter is the rising slope. If I keep this rising slope M1 into the on time. And how do you represent the on time in terms of delta IH? Because again the on time is the band. So, that means, what is the on time? The T on is equal to, that means, T on into M1 is equal to delta I. So, it will be delta IH by your M1. Yeah. So, it is basically delta IH. So, that we have discussed. So, since the ripple is no, now how can we relate the ripple with the switching period? That means, in a buck converter, what is this M1? That means, M1. If we talk about in regular, we know that in fixed frequency it is M1 dt, we know, right. Next, what is D? It is V0 minus V0 divided by V in, and so that means, we have to find out this on time, we have to replace, and we need to basically, okay, let me say, if you have delta IH1 which gives us a time period of T1, then I can set delta IH2 which will generate my time period T2. And since I want to achieve the desired time period, so what I can do, delta IH2 by delta IH1 will be simply T2 by T1. T2 is my desired time period. So, if I set T2 to be my desired time period, then I have to find out for what delta IH2 I am getting delta H1 by T1 into Td. That means, for any arbitrary choice of delta IH1, you will get a T1 value that you can measure using a time to digital converter, and delta IH1 you are only setting from the digital controller. So, then I have to compute just a mathematical computation, what will be my delta IH2 for my desired time period. So, in 1 or 2 iteration you can actually fix it. So, you can achieve programmable switching frequency, and this is very easy because you know that ripple current and the delta H are more or less close, equal. Because of this, they are insensitive to ripple parameter. Programmable switching frequency. Okay. So, you can configure to peak, valley, etc., and very fast transient response, because it is a hysteresis control, right. Very fast transient response, and you can also try other features. So, these are the features you can actually keep on exploring. So, ripple is more or less insensitive. So, these are the benefit that you can get. So, very fast transient response, and you can do trajectory based control, because trajectory based control. So, to get very fast transient performance, you can implement trajectory based control like a hysteresis control and so on, like a sliding mode control also you can implement, because this is a hysteresis band, and then you can generate this current reference from the hysteresis, that means switching surface. So, in summary, we have discussed current hysteresis control with analog loop, current loop, then mixed signal hysteresis control and the waveform, and we have also discussed the benefit of mixed signal current mode hysteresis control. So, then we have covered more or less basic fixed frequency as well as the variable frequency basic architecture, and we have primarily concentrated on the mixed signal implementation, but you can do fully digital implementation, and we have discussed that in the context of fixed frequency control. And in the next lecture we want to summarize this control technique, and in the next week, subsequent week, we will discuss MATLAB implementation of this control logic. So, with this I want to finish it here. Thank you very much.